Okay, perfect. So today's lecture will continue on doing torsion. I'll do a quick recap. And today I also brought a rod. So the idea is, if you see this rod, I basically drew say an element on it. Not the best drawing, but you can notice that how the twisting happens and why certain lines remain parallel and others twist. Say the longitudinal lines, the ones in the length direction, they will twist, but other ones, say in a parallel direction, and the circumference directions, they remain straight. And that was basically one of the assumptions that we basically go off that we use in our derivations. So to do the recap, I go back to the lecture slides quickly, and the idea was, there it is. Yeah. So we started basically with saying, I need to focus on my, there it is. So we have a circular cross section or any cross section, and we have it in pure torsion, so we don't have any other forces on it. So because of that, we could make the assumptions that the stresses in X, Y, and Z are equal to 0, and we don't have any shear stresses in the XY plane. Basically, that's in this case if we just take a slice out of it, is the plane that we see. So, and then we said also parallel lines, longitudinal lines, they basically curve with the structure, and parallel line in circumference direction, they remain straight. And based on that, we had a look at our stress equations because we need to have a look at what the stresses do in this case, and we apply our assumptions to it. And we notice that our stress equations basically reduce significantly to three equations. First, saying that the stresses in xz with respect to z is 0, the stress variation of tau x, tau yz with respect to z is equal to 0, and the combined variation of tau xz with respect to x plus the variation of tau yz with respect to y is also equal to 0. The first two equations basically give us immediately some insight about the functionality of our stresses, and they basically say, well, if the variation is equal to 0, therefore the function must be only our stress must be only a function of x and y. And the third equation gives us a relationship between those two unknown shear stress that we have to solve for. And that is basically what we have to do, is figure out a method how to solve for this third equilibrium equation. And to do so, we introduce a Prandtl stress function of y, and the assumption that we make is that d phi dy is equal to tau xz, and tau yz is equal to the negative of d phi dx. So regardless of which function of phi you now define or use or assume, the third stress equilibrium equation will always be satisfied just by the manner of how it is defined. So now we satisfy the equilibrium equations, and again we come up to the same issue that we had with the stress and strain in the first lecture series. So we had basically, in that case, we had three unknowns, x, y, and z, or u, v, and w, and we had 6 equations, so therefore we needed some compatibility equations to ensure that the solution would be a valid solution. So in that case, we again look at our compatibility equations, we look at our strains, how they are defined, and basically we applied again to our stress equations, or assumptions to it. Stress is equal to 0 in x, y, and z, and tau x, y, z is equal to 0. And based on that, we could basically look at the tau xz, and to look at tau xz, we look at the strain in x and z, and we basically come up with a set of assumptions and observations that we can use in our advantage, saying if the strain in x is equal to 0, therefore the function of u must be equal to y and z, or must be a function of y and z. And if the strain in z is equal to 0, then the displacement function of w must be a function of x and y only, and no longer z. And based on that, we could come up with we could derive some certain functionality of the function of u and v, u, v, and w actually, depending on which variables you take. And based on that, we came up with our basically how our shear strain in XZ and shear strain in YZ must look like. And if we combine that together, we could rewrite it a bit, and then we could come up with two independent compatibility equations that must be satisfied. And if we then plug in our assumption of how tau xz, how the stresses vary with phi, and we plug that back into our equations, then we get this bottom equation here saying that d phi dx squared plus d phi dy squared, and the variation of that with respect to x must be equal to 0. And for this to be true, this inner part means that this inner part must be a constant, and if you take a derivative for the constant with respect to x or y or z, depending on which plane you are looking at, will be automatically 0. So therefore, d phi, the second derivative of phi with respect to x plus the second derivative of phi with respect to y must be a constant. And then, of course, you take the constant, and then it will be 0. So that's basically what we did very quickly last lecture. What we did not discuss is the third aspect of any problem is we looked at the stress equations, looked at the strain compatibility equations, and now we basically have to look at our boundary equations. And for that, we go back to our whiteboard in this case. And hopefully by the end of the day, we'll get through the boundary conditions, and that will be a good way to stop. So, assuming any cross section that we have, we can determine a couple of things. Let's first define our XY coordinate system, and then we can define a certain element on the boundary. And one of the things that we said is that on the boundary, if we look at the XY plane, that the shear forces in XY are equal to 0. That basically means that there's no shear forces in on our boundary. And for that is we basically look at a small element that's dx, dy, and this path is basically nothing else than ds, a small section of it. And you have to take into account that this was part of a rod. So, and we basically took a small slice of dz out of it. So this has a certain thickness that is in this direction, and that's basically dz. Because we often have to go from we have to take equilibrium equations. We cannot do the equilibrium of stresses. So we basically have to convert the forces. Therefore, we have to convert the stresses, multiplied by that area, which is in this case ds, dz. That's our basically area that we're looking at to get a formula to the equilibrium equations. So what this basically means is, if we look at any section of ds around the surface, this must be true. So we basically get a stress-free boundary condition. Yeah.
In this slide, it shows in the diagram there's a delta y, the negative delta x, and then there's a delta s.
Mm-hmm.
So is that a conversion from the cylindrical coordinates to the?
No, just a different notation. At the end, they come the same. You just call it delta s or ds. It doesn't matter. It's a differential element.
Okay.
So from this, if all the stresses on the boundary must be equal to 0, what we get is basically this means that we have a stress-free boundary. Condition. So when we look at our stresses, we call our boundary, our equilibrium equations. Again, so we had earlier and we have also tau xy, respect to y, respect to x, plus direct stresses So these are basically our stress equations, and what we do is basically we're looking at how the stress equations apply to our a differential element within our body. So let's just focus on this segment and redraw this in a slightly different way, so we can see how the equations basically apply to it and how they can be reduced eventually. So we define it as, so if you noticed last time, basically the path S was had a slight curvature, but we can just take a small enough element, so basically represented by a rectangular element. We define 3 points, A, B, and C. And in that case, we define our forces and we define our stresses. So in this case, if you look at this equation, this element, basically what we have to do is we have to equate the shear stresses must be equal to 0. And we also have to notice that we have now given a coordinate system that's basically equal to y or xy in this system. But if this coordinate system transforms, so basically if you shift your element a bit, so you are slightly different location on your cross section, then you still must have maintained equilibrium. So, but take this first, the equilibrium in this case, we take the summation of forces in x and y, and what we get is, I think we have to define a couple of different elements. So this side is, let's call that ds. This will be, of course, dx, and this must be dy.
Are those z's or taus?
Which one? These are taus. Yeah. And there's a small error on the lecture slides, I think. This should be an xc instead of a yc. So it's basically sigma x, xy, tau xc, all with respect to the x, and then tau xy with respect to y, sigma y with respect to y, tau yz with respect to y, and then tau xz with respect to z, tau yz with respect to z, and tau sigma z with respect to z. And these are your body forces, the external body forces per unit volume, x, y, and z. So taking that summation of forces in our xy coordinate system from this system here, what we get is ds minus sigma x dy minus tau xy dx plus x check. Is that double checking why this half x dx dy comes from. Not exactly sure. So this, because now we can write this as, I think that was just an error on the lecture slides if I'm correct. We can divide by ds, get like isolate x, we get tau xy, dx, ds. Yeah, I think that half part isn't on lecture slides. I cannot see exactly where it comes from, so I'm gonna assume it's an error. But we'll discuss that a lot next lecture, if that was an error or some came from somewhere else. But regardless, we can write our force x as a function of sigma x dy ds plus tau xy dx ds. Now what we can do is, just for simplicity, we can rewrite dy ds and dx ds, depending on which angle you choose. You can rewrite that as a cosine and then a sine angle. I think which angle do we use? Not defined. You see, I think theta, yeah. So you can define that as cosine theta and sine theta. And what you can also do is, instead of working with cosine and sine theta, we can work with basically L, M, and N, and indicating that L, M, and N are directional cosines. You see, yeah, cosines. So this might seem a bit confusing, but it's basically done to make it a bit easier on ourselves, because we're going to do a lot of coordinate transformations. So we're going to rewrite this equation as sigma L, or sigma x times L plus tau xy multiplied by m. And later we will define what every L, M, and N is in corresponds with sigma s, cosine theta and sine theta.
dy over ds and dx over ds.
Yeah, so what we do is just take this equation, take sigma x, sigma tau xy to the right hand side, and then divide by ds.
No, the directional cosines, the equation that is above it.
Yeah, so basically what we say is that dy ds and dx ds, yep, I understand what you say, can be written as a cosine or sine, yeah. And then if we do this correctly, what we can do is we can extend this to the y-axis and to the z-axis, and what we get is the forces x, y, and z as function of the directional cosines. I'm going to write this out because we will need them for later. So this basically corresponds, if we do take this element and we look into an x, y, and z coordinate systems, and we basically derive the same equilibrium equation for a 3D case. So in this case, this was a simplified 2D case. We'll get those terms, we get those body forces as part of the stresses in x, y, and z, and corresponding directional cosines. So we go back to this drawing here and go back to what I mentioned earlier, is this must be true for basically along the whole the whole boundary of the element, and recall back that we basically took this small element. So if you basically now shift this element or rotated this element, then the condition of the stress-free boundary condition still must be upheld. So that means in order to maintain that stress-free boundary condition, that means that, let's redraw this. That means that our triangle that we defined x and y, and if we basically rotate that, to our new coordinate system, that's basically x dash y dash then still our directional cosines must be true. And of course, we assume there's no body forces acting on it. So taking back to this 3D, say equations, and our stress equations in 3D, in our most generic case, if we assume there is no basically forces acting on it, then this of course must be equal to 0. And if we assume that we go back from our 3D case to a 2D case, we can also ignore the variation with respect to z. So what we get is basically only this part. So 2D case becomes sigma x times L plus tau xy times m, sigma y times m plus tau xy times L is equal to 0, is equal to 0. And then, since we have a 2D case, this was on our x, y axis. So this must still be true in our x dash, y dash axis as well. So, and to do so, we use the stress transformation matrices that we did in our one of our first lectures. So what we do is then we rotate that, and if you remember correctly, our rotation matrix I think was, if I remember correctly, was cosine sine 2 times cosine sinus, then all that stuff. So what we do in this case, we rewrite that again as form of directional cosines, and we say that so this equation we see basically represents what we had earlier, that we had in coordinate transformation that was, I think, by heart, something like this, to cosine theta sine theta, and then sigma x, sigma y, tau xy here, and here we had our xy, tau xy, now dash system. Sine theta minus there was cosine squared plus theta plus sine squared theta cosine theta sine theta. I think something like this. I don't remember it by heart. Pretty sure about these four and that one, but off diagonal terms. So you can rewrite this equation, represent that by directional cosines, and basically means that if you do an index notation, if you had with a continuum mechanic, then this will be a bit more familiar. So there's nothing else than a coordinate transformation going from one axis system to a different axis system using directional cosines, in this case L and M, which corresponds to basically your cosine and sine theta.
So in the third column, there's a blank in between. There's nothing there.
No, there's something here, but I don't remember that. So the terms I am pretty sure that are correct are these four.
Those are squared.
And this squared I'm correct. I think this one is a 2. I don't remember the other ones.
Those four terms are squared. All of them, the plus squared.
Oh no, this is cosine theta squared plus sine theta squared.
No, I'm talking about the four terms of cos theta, sine theta, negative sine theta, cos theta. I think they are squared. I have it written as squared.
These ones?
No, to the left.
This one?
Yeah.
Oh yeah, they're squares here. And they're definitely squares here. So, but you can look back into the lecture slides or what that exact coordinate transformation looked like. But my point is, you can represent that by directional cosines and index formations. Because there's a lot of coordinate transformation that we apply, and going with the cosine sine theta it can become confusing. So we're going to use the directional cosines L and M, and L subscripts M and P to define which coordinates we're transforming around. I'm going to erase this because I'm pretty sure this contains some errors. But with that said, if you then do a coordinate transformation using this in mind, let me see here. We can get a new coordinate transformation of sigma x in our new axis, and that will equal to Lxx, Lxx, sigma xx, 0, and tau xy is equal to 0. So what this means basically the angle between the x component, the angle between the your original x component, the new x component, multiply that with the angle of your new component, and your traditional component xx, that should be equal to 0. And similarly for y, so it's x with respect to new x with respect to old x, and yx with respect to the old y. So those coordinate transformations should be equal to 0. And that luckily corresponds to what we had here as well. So another angle that basically now with x sigma y, so we have to deal with tau x z and tau y z. So these are basically pointing into the sheet. So I will draw them as crosses. And now we have to define these two shear stresses as well in our new coordinate transformation axis. So yeah, so let's do that. See here. So in our new coordinate transformation axis, when we do our transformation, this will be equal to xx, yx, sigma xx plus, and I will do only one of them. So this will be our equation. Again, this is the genetic one. So we recall that we had a couple of assumptions that were basically equal to 0. And we also didn't have tau xy is equal to 0. So we can ignore this part, that part, this part, and then tau xy's. So this should be y tau xy, so this one is equal also to 0. And then we are left over with the tau yz here, tau zy, tau xz, and tau zx. And we also know that basically our stresses are symmetric, so tau yz is equal to tau zy and tau x. So tau xz is equal to tau zx. And then we can define our angle theta. So this is angle theta, then this angle must be equal to theta, and this angle must be equal to theta. And I'll go to the lecture slide for this one, because it's just a lot of writing. So eventually, if we do our coordinate transformation correctly and we define all angles correctly, what we can get is that we can note that the angle transformation between original or new transformed x-axis and y-axis is equal to 90 cosine 90 minus theta, which is sine theta. Our angle transformation between the original and new z-axis, because you're transforming basically around the z-axis, that angle is 0, so the cosine that's cosine 0, so that's equal to 1. Coordinate transformation within the respect to the new and new axis with respect to the z-axis is cosine 90, that's 0. So basically we can write these coordinates that we had, or these transformation directional cosines that we had earlier, now as in form of cosine basically 0, or cosine theta, or sine theta. And because of that, this bottom equation that we basically derived for tau xy, the shear stresses in our new coordinate transformation, basically can be reduced to a function of sine and theta. So our new transformation coordinate system here, let's write that on top, xy in our new coordinate system, xz, sorry, is equal to tau yz sine theta plus tau xz cosine theta. And then we can basically we can repeat the same procedure for tau yz, and we can also repeat the procedure for any other coordinate axis that we are interested in. But if you remember correctly, we said we have a stress-free boundary condition. So even if we rotate, this must be equal to 0. So this basically means that this equation must be equal to 0, because we still are on the boundary, and we said that we don't have any stresses at the boundary. So this must be equal to 0. So what we can do is we can just rewrite this a bit to tau yz. So let me see. Yeah, we divide by cosine, so we get here 1, and this what we get is tangent theta plus tau xz is equal to 0. And then what we can do is rewrite it a bit more. We can get a function for tan theta is equal to minus tau yz over tau xc. Get rid of some of the so now we have basically a tan of theta equals negative yc over tau xc. We're getting there. We need a couple more steps and then we can draw a conclusion. So we can rewrite, you can use this formulation to basically rewrite our previous equation as tau yc multiplied by negative dx plus tau xc multiplied by dy is equal to 0. And what we can do is, in the earlier slide, we had basically, I should look it up again. We defined the variation with respect to, we defined the direction cosines of dy ds, remember this correctly, and dx ds. So I want to go back to that later step. So we can basically combine that with our function phi that we had earlier defined, that we said our Prandtl stress function of phi equals that up. Yeah. So we had also d phi dx, which is equal to tau yc, negative of this, and then we also had tau xc equal to d phi dy. So this was the Prandtl stress function. So we want to basically find a way that we can incorporate this into this equation. And to do so, what we do is we divide both sides with the s. So we get tau yc dx ds plus tau xc dy ds is equal to 0. And we substitute in these two terms into tau yc and tau xc. So what we get is that d phi dx multiplied by dx ds plus d phi dy multiplied by dy ds is equal to 0. So now we can just change, this will cancel out. So what we get is that d phi ds is equal to 0. So from the boundary conditions, might be a bit confusing, especially the cosine, directional cosine, and the directional cosines might be confusing. Now to do the transformation axis, basically every L and M stands for which two axes you take that angle with, and how that transformation works. By the end of the day, this is the important step that we get from it. So if you take the boundary conditions and we want to apply the stress, the Prandtl function to it, we'll derive to a fact that says that d phi ds is equal to 0. So let's have a look back at what actually ds was in our original drawing. So if we had our cross section, we had an axis system. We said this is x, this is y, and we can look at a small incremental element at any location. So we have a dx, dy, and this path as our ds. So in this case, if you look at this section, this path is ds here, and over here we have another ds. So what this means basically is that our frontal stress function phi along the boundary, so d phi ds, basically meaning if we take the derivative and we look at it with respect to the boundary conditions, must be equal to 0. This again goes to the fact that we stated here that if we look at the small element, if we look at the differential element and we say that we define our stresses x, y, and z on it, and we look at a 2D case, then we know that our stresses x and y are equal to 0 because we have basically we don't assume those stresses to exist, and that tau xy is equal to 0. We said this leads to a stress-free boundary condition, and this stress-free boundary condition is defined by the fact that our function phi over the boundary must be equal to 0. And now we can look back at what we defined here. So let's go back to this. So we had our Prandtl function that basically said our x z is d phi y, our yz is the negative d phi dx, and we said that they're on the boundary d phi ds is equal to 0. Well, the variation with s must be 0, so basically, so we can also see that this statement that we got eventually from the boundary conditions basically do not affect what we earlier had assumed that our stresses look like, since this is only function of respect to x and y, while this is functional with respect to the boundary s. Let me see. We have 20 minutes left. Okay. I'm going to go back to the lecture slides just for simplicity, so we don't have to draw too much on the board. So basically this is what we said. So our d phi ds implied that our chosen stress function is constant, or constant in this case, and did not affect our stresses, how we derive it, because their derivations with respect to x and y. So the function phi must be 0 on a bar boundary. So the last step what we have to do is, since we are talking about torsion, we want to have basically everything also related to a torque or to an applied moment that we are dealing with. Similar to our engineering bending equation, where we basically eventually at the end of the day we turn back into the moments, where we took the integral of the forces or the stresses to create a moment and relate that to an applied moment. We want to do the same for the torsion case as well. And to do so, we're going to look again to an arbitrary point in our cross section. Let's call that element dx dy as a squared element. And we basically know that on that point, we all have our two stresses acting on it. That's tau yz and tau xz. So if you take the integral of that, or we multiply by the area dx dy or dy dx, we get our forces in the x and y coordinate system. So why not basically go ahead and relate this to a torsion or to a moment. So what we do is we take the derivative, or we take the integral of every small element on that cross section, and we basically multiply that by an arm, and we define basically in coordinate system. In this case, clockwise. Let me see. Tau y z. So counterclockwise positive. That's the reason why we see here tau I z times x. That's basically the moment, the force times the moment arm x. So tau y z multiplied by x, that creates a moment, and tau x z multiplied by y creates a clockwise moment. This creates a counterclockwise moment. Counterclockwise is positive, so we see a positive here, and we see a negative sign here for tau x z times y. And in order to basically sum up all the forces and all the moments created by all the differential elements on that cross section, we take the integral with respect to the area. So that's going to be substituted by a double integral with respect to the x dy, and we basically can evaluate that function that we defined earlier. So the torque, the torsion is equal to the double integral of tau xy, tau yz with respect multiplied by x, minus tau xz multiplied by y dx dy. So again, we substitute our Prandtl function in for tau yz and tau xz as phi d phi dx and minus d phi dy. So that minus cancels out with the initial minus, so it becomes a plus here. And where we get is our torsion going in our given direction. So, and this torsion, due to these two shear stresses in our body, in our cross section, must of course be equal to the applied torsion, because there's otherwise no other forces acting on a body. So what we can do, we can solve this integral by integration by parts. We can see that the integral of x d phi dx with respect to x is equal to x times phi minus the integral of phi with respect to x. Similarly, you get the integral of y multiplied by d phi dy with respect to y is equal to y phi minus the integral of phi dy. So we know that on a boundary, our stresses, variation with stresses with respect to the boundary is equal to 0. So our stress at the boundary must be equal to 0. So we can basically plug in, ignore x phi and y phi in this case. And if you plug that back into our torsion equation, we can rewrite it, and we can see that the torsion must be equal to double integral phi with respect to dx dy and twice this value. So at the end of the day, to solve a torsion problem using the Prandtl stress function, we must satisfy a couple of things. We, per definition, know that tau yz is equal to d phi dy, and tau yz is equal to minus d phi dx. So we can define a function phi that has this form for the shear stresses. At the same time, if our function phi satisfies that the second order derivative of phi with respect to x plus the second order derivative of phi with respect to y is a certain constant, then our function phi is valid as long as these two secondary statements are true as well. So we solve this equation here while maintaining that phi on the boundary is equal to 0 and that applied torque is equal to 2 times phi dx dy. If all these conditions are true, then basically our solution phi can be assumed to be correct. If any of those are false, then the form of phi that I've chosen for the problem is not satisfactory. can be either that you didn't take into account that the stresses on the boundary will not be satisfied, or the compatibility equation will not be satisfied. I think actually this is a good way to stop here, because we had a lot of information. Let me see. Yeah. Actually, let's continue. We just deal with the solids for in this case. Just to continue on a faster pace, we're going to continue on the lecture slides. So the next thing, so what we discussed so far for torsion is from a solid bar is we looked at the stress equations, we looked at our compatibility equations, we looked at our boundary conditions, and we basically from those three we got a set of equations that we had to satisfy of our function phi in order to be a valid solution. So another thing that we have to deal with the solid bar is the twisting angle. And for that is we're looking at a small representative beam. Again, you can use it as rod, clamped on one side that doesn't move, and the other side you apply a torsion to it. And if you draw a line from A to B and you do it pre and post tension torsion, you will notice that this angle A on the free hand side where you apply the torque to it has moved from location A to location A1 or A dash. And that angle between the pre and post torque applied to it, that angle is basically your angle of twist. And we can say in this case for solid bar clamped on one side, that angle can basically linearly vary with respect to length. So we know that the function theta is equal to theta x, where x is the location area length, divided by the total length. So with that in mind, we can basically look at our shear stresses, and we can define another coordinate. That coordinate is called rho, and rho is basically defined from your origin to A. So it can vary from 0 to the maximum radius r. So in this case, our location shear stress is equal to rho times theta divided by x, divided by L. So we know that if rho is maximum, it varies from 0 to r, which r is the radius of the circle. So it's maximum at the outer point of the circle. So maximum shear stress will occur at the outer part of the radius. So the maximum shear stress equals to r theta divided by L. And we also, again, we assume basically linear variation between the in-plane shear strain. So if you have any location halfway between 0 and r, you can just say rho over r multiplied by the maximum gives you your shear strain at that location. So we know if we go back to Hooke's law, we know that stresses and strains are related to the shear modulus. So we can look at the stresses as well. So for the maximum stresses to occur is the shear modulus multiplied by r theta over L. So, and again, if we look at any location between 0 and r, we just divide, we know that the stress is equal to a ratio of rho over r with respect to multiplied by the maximum stresses. So again, what we want to do is relate this to torsion, because we want to eventually solve it for a given applied torque to it. And to do so, we say that we basically find the resultant moment in the cross section, and we set this equal to the applied torque. So we multiply tau with respect to rho dA, basically force times area, and multiply by an arm. So we can rewrite that as rho squared r tau max dA, and we set that equal to our torsion. So we take, again, if you want to do it across a whole cross section, you basically take an integral over the area. So we get is that the integral over the area of rho squared r multiplied by the maximum shear stress dA is equal to the torsion. So we know that the maximum shear stress is non-zero, or at least a constant not varying with the area. We know that r is again also a function that a variable that doesn't vary with dA. So we can take the stress over r out of the equation, and we can define the torque as equal to the basically tau max over r multiplied by the integral of rho dA. And rho dA, if you notice it, is very similar to our y squared dx or x squared dy or etc. So this again a form of is basically another form of moment of inertia. In this case, since we're talking about a torsion, we call this the polar moment of inertia, and that's defined as J is equal to the integral of rho dA, rho squared dA. And rho is again your location from your center, from your centroid to any location on your circular bar. So with that said, we now can say that the torsion is equal, or the torque applied is the maximum shear stress divided by the radius multiplied by our polar moment of inertia. Again, we can rewrite that if you're interested in shear. We can say the maximum shear stress occurs at torsion multiplied by the radius r over the polar moment of inertia. And if we look back again, a couple of slides, we had the function of the maximum shear stress as a function of the shear modulus, the length, and the radius, and the angle of twist. So we can also rewrite this in a slightly different format. We can say that the maximum shear stress is equal to the shear modulus multiplied by r theta over L, which must be equal to the torsion multiplied by r over J. So what we can do is we can cancel out the r's because it's basically the radius drops out, and we can rewrite theta as a function of our torsion, our length L, our shear modulus, and our polar moment of inertia. And the reason why we want to basically isolate theta and not say torsion, or in this case, is because the angle of twist, which theta represents, can be a requirement, a design requirement. In many cases, you have to design for a given stresses and loads, what we had in the bending case, and torsion you often have to design for maximum angle of twist. So your structure can only twist a certain amount of or have a certain amount of twist to it. Any more twist than a prescribed angle of twist, it might fail, or you get a complication in that you damage something. So that's the reason why that's important. And you can see that the angle of twist is of course maximum at the end. That's because we already said that the twist is linearly dependent with respect to the length. So if we have an 1 meter bar, the angle of twist at the end of 1 meter is different than at say 10 centimeters from the clamp. So because of that, we can also define something that's basically looks at the variation with respect to the length. So we look, instead of theta, we look at the rate of twist, so the theta dz. So if you take then the theta dz is nothing else than basically differentiating with respect to L, which is in this case the z direction. So the theta dz is equal to the torsion divided by the shear modulus and polar moment of inertia. And then of course you can also write the torque as that, so you can just, if you have a given rate of twist that you cannot violate, and you have given a cross section and shear modulus, you can find out what the maximum torque it can handle. So these equations are all the same. It's just one is it depends if you isolate torsion or rate of twist. In both cases, both can be asked for on a question. Sometimes you're given torsion, you have to calculate rate of twist. Other cases, you have given a rate of twist and you have to determine the torsion applied to it. This is actually a good problem. We have only 5 minutes left, so I'm going to leave it on the board, and we can discuss this problem in the next lecture. So in this case, let me see. You have a circular beam loaded in torsion. Origin is given. In this case, basically tau x z and tau yz is given as the constant a times y and a constant a times x. And basically you have to use those two given shear stresses to determine the applied torsion on the beam. So assume that your phi we basically represented tau x z and tau y z. So d phi dx, oh no, d phi dy is equal to minus a y, and d phi dx is equal to ax. So idea is to come up with a stress function and see how that torsion is applied. Okay, are there any questions? No? Okay, thank you.